Good. So, before I actually start lecturing, just a couple of quick questions from you. Maybe I'll have to ask them again when more people come. Okay, I'll stop sometime in the middle, and I need to know who's registered and how we're going to evaluate this course, who is taking this course for privilege. But I think let's give 5 more minutes to the question. Okay, so let me start today's lecture. So far we've been discussing in fairly good amount of detail the vacuum solution of this equation that's described, that's spherically symmetric and described by the Schwarzschild metric, and we analyzed the metric in various different ways and came to the conclusion that it's smooth at the horizon, it's singular at the origin, and that when we pass through the horizon, something happens to the causal structure of space-time, which makes sure that you can go in to that thing, but you can't come out from it. And that's why we call this object, such an object, a black hole. Now, of course, it need not be a black hole if it has a radius of matter up to some large distance greater than 2 gm. In that case, it's a Schwarzschild solution outside and completely harmless solution. And inside, it will have some matter. And this matter may or may not, depending on the situation, collapse and go inside the horizon. And only after, if it does, then all kind of things will take place. Because once the matter is inside, then it is subject to the same force which we already saw propels any particle to the center in a finite time. So imagine that there's some distribution of matter. So in other words, what I'm trying to say is this: a naive picture, which is not correct, would be that this is the horizon. Now suppose the matter distribution is everywhere here. Then of course the existence of the horizon is meaningless to us, because all we can say is that outside this radius there is a Schwarzschild solution. This is not naive, this is a correct picture. What's naive is to say, okay, the opposite situation is that there is some matter sitting here inside. Okay, so this one is, of course, this is correct, this is not a black hole. But this picture itself has something wrong with it, because it's not possible for a lump of matter to just sit inside the horizon of a black hole. There's somehow an implication in this picture that it's sitting there in a time-independent way, but that's what it can't do. Because consider each particle of this supposed matter distribution. Each such particle has a law governing it, that dr by dt in the infalling direction is greater than 1 over something I derived last time. I think this is the right expression. Right? Remember, I found a bound on dr by dτ. This is tau, its proper time. So that means that this entire shell, the outermost shell of matter, sorry?
It's probably d tau by dr.
Because it's dr by dτ that needs to, it's dr by dτ, it's only that this is substance. Has to be d tau by dr is bounded below, right? That's a minimum velocity. If d tau by dr was bounded below, then it would be a maximum velocity. The whole point is that this is incompatible with r being independent of tau. Okay. So any particle that's inside here is not allowed to stay there forever in its own proper time. It has to move radially inwards. That means every shell is going to move radially inwards. That means applying exactly the same analysis that we already did to each particle in this whole thing is going to be in a state of collapse. It's going to keep moving in. Okay, so this, really speaking, going to be a dynamical situation. So naive refers to the idea that everything just sits over there. Okay. if you were to believe in the naive picture that there's a lump of matter sitting inside the horizon, then of course you could say, well, after that the solution becomes regular up to the horizon. Exactly as we say here. We say that up to here outside there's vacuum, and when we cross this matter boundary, then the solution is regular inside. That is true. But in this case, that argument doesn't hold that it's regular outside this, and it is regular outside this, that much is true. But it's not the case that the presence of matter just masks the singularity completely. Okay? Because the matter can't just sit there. The matter is continually in a state of falling in, if there is matter inside. So just a comment, yes.
Suppose during that time there is no problem.
Yeah, but it's a time-dependent situation.
Okay.
Okay. So the point is that it's not something static. This is something completely static. But in fact, what's happened here, as you already saw, is that the radial direction inside the horizon is time-like. It's no longer space-like. Okay. And then coupled with this bound, you see that this cannot be some static situation. That's all I'm trying to say. Just a very brief bound. Okay. So now, with all that in mind, we want to introduce, finally and for the first time in practice, some energy momentum tensor and try to solve these equations in the presence of an energy momentum tensor and ask how it affects the picture we already made. In particular, though we won't actually write it down in complete detail, in particular we expect there should be some solution compatible with the first picture I drew, namely vacuum outside some radius r tilde which is greater than the horizon, and then some non-singular solution, perfectly non-singular all the way to r equals 0 inside, and that you could call a star. That would be a reasonable thing to call a star. Okay, completely non-exotic object, but described in general relativity in a particular way. Okay, so that should be there, and we'll argue at least most of the argument that it should be there. I'm not sure if I can actually complete the argument. So now the question is, what do we put for T mu? What can T mu be? So we saw that fundamentally what T mu is, it's the energy momentum tensor of some system of fields. So for example, it can be a half d mu phi minus some extra terms for a Klein-Gordon field, or it can be something made out of gauge fields. Again, there are different ways to contract the indices, but something basic. It has to be second rank tensor, and for a free field theory, it's just piling in the field. So in Klein-Gordon theory, it's like this. In Maxwell theory, it's like this, and so on. Okay, so you can have various energy momentum tensors for any given field theory. But of course, if you put that in, what you will get is a coupled set of equations for the gravitational field and one of these other fields. Then you also need to write the field equation of that other field, which could be the Klein-Gordon equation or the Maxwell equation, and you need to solve the coupled system. Okay, so is that clear? That's sort of the most general thing you can do. So you get coupled equations for the metric and phi, a scalar field or vector field, etc. The classic application of this would be if this is the energy momentum tensor for the electromagnetic field. In that case, you could solve this equation and you could get, for example, a charged black hole. You could find a classical solution that describes the charged analog of the Schwarzschild black hole with an electric charge, and then solving the Maxwell equation in that background would give you the electric field or the magnetic field of that charged black hole. So you would solve simultaneously for the metric and the field. The metric is one field after all. Okay, just think of what's a general charged object? It's got a mass, so it's gravitating, so it has a gravitational field. It's also got a charge, so it's giving off an electromagnetic field. So these kind of equations are coupled equations for both these fields, and the solution will tell us the gravitational field and the charge field, right, the electromagnetic field, and any other fields of the object. But of course, this is not what we always want to do. We often want to just treat the energy momentum tensor, almost always actually, treat T mu nu as an effective quantity generalizing its 0,0 component, which as we know is related to density. If you remember how we started to discover general relativity, it was by noticing that T00 is related to matter density. So we wanted, now here in this case, T00 is also given by something made out of fields, but we don't have to know that. We can just say, let me take matter of a certain density. Okay, then I forget where that density came from. It came from some other fields. I don't worry about those. I just treat the density as an independent variable. This is what I mean by effective quantity. You see that? In reality, all densities in nature are due to some combination of fields. All densities, even the density of water. But of course, when we study water, we are not so foolish as to say, well, water is made up of fermions and bosons and its density 1 gram per cc is some condensate of these fields. We just say the density is rho of x, and in normal conditions it's 1 gram per cc. So we just make that the independent variable, and with a few independent variables we can then write these equations and solve them. However, there's one price to pay. If you treat various parameters in T mu nu as independent variables, then you won't get enough equations to determine all of them. Okay? Because what is this equation supposed to do? It's supposed to determine G mu nu. You can't expect it to determine everything for you. It is many equations because all the values of mu and nu. But finally, you need some internal relations among the variables of T mu nu, and those relations are generally known as equation of state. Okay. What we'll see is that in the most simple, typical situation, rho is generalized by the addition of pressure, and the two variables are density and pressure, and then there's a bunch of equations which tell you the gravitational field for distribution with some density and pressure, and there are also relations among the density and pressure, which is the equation of state. Once you have all of those, then you can solve for the whole system. Okay. Good. Now recall, so let's see. I need to do a couple of things about the energy momentum tensor before we get down to this. First of all, let's recall what happens in flat space-time where special relativity applies. Okay. So let's assume that we are not thinking about gravity for the moment, but that T mu nu describes some perfect fluid of matter, and by perfect fluid we mean that it doesn't have things like heat, so we neglect heat conduction, viscosity, dissipation, and so on. Let's also assume that this perfect fluid, so this perfect fluid has a velocity, and let's assume that we are working in its rest frame, so the velocity, okay, before that, let's also assume that the fluid is isotropic and homogeneous. And under these assumptions, it's very easy to guess that T mu nu basically has one component we've already seen, that it's density rho, But there are three more diagonal components and they are all equal and we call them the pressure. So these are functions of x, y, z and t. The reason why these are all equal and the off-diagonal ones are 0 comes from isotropy and homogeneity. The fact that this part, the 3 by 3 part, is proportional to the identity matrix means it's completely invariant under SO3, which are rotations of space. Okay? And is the only matrix with that property which uniquely fixes that has to be proportional to a single function. So that function we call P, and we'll see as we go on, and you can see in many other ways that it's really to be thought of as the pressure. So the two variables for such a system are density and pressure. And now we can ask the question, what about general space-time? Okay, and this was also in the rest frame. What about the general space-time? So there's a nice trick which allows us to generalize this formula to an arbitrary space-time with a metric G mu, which is the following. Given a perfect fluid in any space-time, T mu is a second-rank symmetric tensor. Okay, the perfect fluid is characterized by its velocity 4 vector. U mu, doesn't matter here whether it's up or down, but it starts like as having one index up. Okay, so T mu being a second-rank symmetric tensor must be determined either by some property of the space-time, which is a second-rank tensor, or by the velocity. And it's easy to see that these are the only two invariants that you can have. Now, in principle, I'm not sure why you can't have higher dimensional invariants like R mu and other bilinears made out of R, but I think the assumption here is that it doesn't depend on derivatives of the metric. So in this case, we just have to reparameterize this matrix in terms of this by keeping in mind.
Argument for double derivatives of metric?
Yeah. I think the basic argument is this, that we are thinking of a situation where fields are slowly varying. Okay? It's actually also a similar argument for studying Einstein's equations at all. They are the equations from the action root gr, but nobody stops you correcting that action by a term root g times r squared, or root g times r mu lambda rho r mu lambda. So in principle there could be corrections to Einstein's action and there could be corrections to these things. But we simply won't consider it. Okay. Now u mu is the velocity for vector, and in the rest frame, so u mu has to satisfy u mu. Sorry, I'm still in flat space. I haven't yet gone to the general space. So in flat space, u mu equals -1 implies that u mu is the vector 1, 0, 0, 0. Right, each particle of this fluid is massive, so the massive condition is p square equals -m square, which becomes u square equals -1, and so u is that. And from that, we see that my notes I've done it with t upper mu, so I hope I don't get some sign wrong, but I think it's okay. In any case, now t0, 0 therefore is alpha times u0, which is 1, and minus beta, because beta 0, 0 is 1, while tii is simply beta, because u in the rest frame is 1. Okay, so I compare this with these.
What is the sign of the metric? Is it minus plus plus?
It's minus plus plus plus. It has been since the beginning of this course. Okay. Good. So in this parameterization, alpha and beta are related to T00 and Tii like that. But T mu nu is also this diagonal matrix. So we can compare, and by comparing this, we see that T mu nu is actually P plus rho mu plus P eta mu. Okay, so this has the desired property. Because alpha minus beta is T00, which has to be rho, and beta is Tii, which has to be P. So this is correct. Okay. But now this equation, which I have derived in the rest frame, is completely covariant in special relativity. So it can be valid in any frame where u mu is the velocity in that frame. Moreover, its form manifestly tells me how to generalize it to general relativity, because u mu concept still exists. I just have to remember that u lower mu is lowered from this with the metric, and eta has to be replaced by the metric itself. So this is much more complicated, because now this object can have a dependence on space-time coordinates through the fact that g mu nu is not constant. Okay, but this is the general formula for the energy momentum tensor of a static isotropic homogeneous fluid, and now we can just try to use this to solve Einstein's equations in the presence of matter. Okay, so is that clear? Earlier it was 0. Now we'll get some new solution, but that new solution, if I put P and rho to 0, should go back to the old Schwarzschild solution. Yes?
Where does is introduced that particle assumption?
Yeah, so that assumption basically, so let's see. Yeah, so if it wasn't a perfect fluid, what would change in this? So, sorry? Yeah.
Because the Tij's will then have other, you will recognize Tij's as pressures.
Yeah, I think the question is, though, we are talking of, we are assuming it's isotropic and homogeneous. That's what fixes the off-diagonal.
The Tij is basically stress tensor, so that will probably give out other terms.
That's correct. But I'm just trying to understand, probably the question was what aspect of perfect fluid, if I violate, what will, so if I, for example, if I allow heat conduction, viscosity, whatever, yes, it's clear that I'll get other components of the stress energy tensor. But if you ask me now exactly which components for which thing, that I probably can't. It's probably, I think it's well known. So
that's the call where we are taking the combination of u mu, p mu.
Yeah.
In T mu.
No, this doesn't rely on any of this. The point is, this is the form depending only on two functions, rho and p. That is the statement of homogeneous isotropic perfect fluid. Okay? Actually, we can take it almost as a definition if we like. Then we have to convince ourselves that it's a reasonable definition of stress energy tensor for such a situation. Okay? This is general for something that's characterized only by its velocity. Now, if the fluid has some other thing characterizing it, then that thing could appear here. Okay? As long as it's characterized only by its velocity 4 vector, then that and this invariant of space-time are the only two second-rank objects we can make. Anyway, this is all motivation to finally end up with this T mu nu, and now we need to solve Einstein equations for that T mu. Yes.
In the final equation, is it homogeneous because it is a function, G mu is a function of x and t?
Yes. So the point is that the question then is, what do you mean by homogeneous? Okay, homogeneous is very clearly defined in special relativity in the absence of gravity, because it says look around you, every direction is the same. Okay, that's isotropic. Sorry, homogeneous is translate yourself to another place, physics is the same. Now, general relativity doesn't actually say that anymore, because if the metric is non-trivial, for example, I am the metric of the sun, then I translate myself into the core of the sun. Obviously, life is not the same as outside. So what we are doing, so there are two ways to think of this. One, probably the correct way, is to define all these concepts in the language of tangent frames to the manifold, which since I haven't introduced for you, I can't do that now. Another is to say, let's assume T mu nu corresponds to such a fluid in flat space-time, and let's generalize its form to an arbitrary curved space-time, just requiring it to remain a second-rank tensor. In other words, this one is the energy momentum tensor of a homogeneous isotropic perfect fluid, and this one is this GR version. You could argue that. Okay, because after all, GR, the whole point of GR is that there are gravitational fields around, and gravitational fields violate the homogeneous and isotropic thing. So it's, in some sense, it's still homogeneous and isotropic, but only because of the metric. It doesn't have its own. It doesn't make its own contribution to inhomogeneity. And the best way is to just say that this is the definition of such a stress energy tensor. It's a very reasonable definition.
Means any kind of inhomogeneity or non-isotropic, because of metric we don't care. Anything else don't.
We don't care in the sense it's not in our control. It's part of space-time.
I mean, yeah. Then also we can call it a homogeneous.
Yeah, I really don't think it matters what we call it. I suppose we could call it that. What matters for me at least is this equation. Yes.
We also have to put in the eta mu term, but eta mu wouldn't have anything to directly do with the fluid.
Yeah, that's true.
But since they are true on the most.
Yes, that's correct. But also, I mean, this is the answer already in the restaurant, right? First we concluded this. So then this, of course, can be parameterized like this. Okay. If you want to understand the energy momentum tensor more in detail, I refer you to Hartle's book, which has a very nice detailed description of all the physical meaning of the energy momentum tensor. Maybe many of your questions are answered. Now, one thing I want to mention here as a slight aside, which is that although we are going to solve the equations R mu nu minus half G mu nu R equals 8 pi G T mu nu, there's another term that we could have added to the equation, which is the cosmological constant term minus lambda by 8 pi G. That's all. Did I get it right? No, probably not. Sorry, plus lambda on this side. That's all. Lambda G. Well, lambda is a constant. Okay. Now the interesting thing is that this is the full equation, but supposing space-time were actually there was no matter, so T mu nu was 0. But if I took this term to the right side, I could convince myself that this is also a form of an energy momentum tensor. Okay? So, solving the equation in the presence of lambda as well as t, or only lambda or only t, it's sort of the same, except that lambda introduces some new contribution to the energy momentum tensor. So, lambda G mu nu can be thought of as a new contribution to T mu nu by taking it on the RHS. However, it would be a somewhat strange contribution because for this contribution, so let's write out T mu nu due to the lambda term, due to the cosmological term, is equal to 0 times u mu nu plus, actually in this, if I take it to the other side, then minus lambda times g mu nu, right? Because it is minus lambda times g mu nu, so the contribution that might have been there proportional to u mu nu is simply not there. If we parameterize it in the language of pressure and density. Okay? Therefore, effectively, for this cosmological constant term, rho is equal to minus P. The pressure and density are equal and opposite, which is why they cancel here. And we identify lambda with minus the pressure or plus the density. Okay. Now you could argue that this is very strange because how can a perfect fluid have negative pressure or negative density? It can't. And that's because this term isn't the energy momentum tensor. It just behaves in the equation like an energy momentum tensor. So it's convenient to think of it in the language of pressure and density. Okay. But it's not the energy momentum tensor of any field. If anything, it's part of the story coming from gravity itself. Okay, and it's a part which has a very characteristic signature of having density, effectively the contribution to density and pressure variables being equal and opposite, and being proportional, actually equal to the value of the constant lambda. So it's constant pressure, constant density, and pressure is equal to minus density. It still leaves open the question whether this density is positive or negative depending on the sign of lambda, because lambda is we are allowed to choose the sign of lambda. Okay, so you should think that merely that it behaves in equations, the cosmological term behaves like a contribution. If it behaves like that in equations, it will behave like that in experiments too, like a contribution to T mu having constant. So this is certainly not a general characteristic of T mu. The rho and p need not be constant. But one can easily anticipate that with such a very striking property, it should be possible to pin down with experiments whether this is actually the case. That is to say, if an experiment detects something that we compute from solving this equation, and it finds that effectively the pressure and the density are coming out to be constant and equal and opposite of each other after subtracting all other effects from all the other energy momentum tensors contributing in that experiment, then it would be telling us that such a term is present, and the value of the rho that it finds as well as the effective sign of rho, which can be both ways, would determine lambda. And today we know that lambda is a very small positive number which you can find in books, and it's a very interesting open problem in gravitational physics, why it's there and why it's so small. It was thought to be identically zero, let's say even right through the mid-80s it was assumed that it was identically zero, and now experimentally we know that it's not. Anyway, that's not the goal of my disha. Here's the value. So rho, experiment tells us that rho of the vacuum, it's called rho of the vacuum because T mu, suppose we assume T mu is 0, okay, so then it's the rho which is actually the same as lambda, so that's what we call rho of the vacuum, and experimentally it's determined to be in energy units, so it's a density 10 to the minus 8, I think, ergs per cc. And this can also be written in energy units where it's a little more striking. It's 10 to the minus 12 GeV per fourth. You can convert the 3 length dimensions in the denominator to energy units in the numerator, so you get 4 powers of energy. Okay. It's also obvious from the fact that lambda multiplies integral d for x. Integral d for x has 4 units of length. So to cancel it, it must have 4 units of energy, 4 powers of energy. And that's the scale. The point is that this is not a scale familiar to us in particle physics, where the fundamental scales are typically masses of particles, or they're the interaction strengths or the weak interactions, strong interactions. All of those are way up in the EV and above EV range, GeV, GeV, now EV range. But nothing is, this is 10 to the minus 12, so 12 orders of magnitude down from the range of typical values, and then 4 to the 4th power. So it's a very strange problem, why it's so unnaturally small. Okay. Good. That was a digression, but a good one to make, because then we can forget about this term and do this with a T mu parameterized in terms of pressure and rho, and if we feel like solving the equation with a lambda, we'll just put P equals minus rho and we are done. Just a special case. Before I start that, now that everyone is here, so following a few announcements. First of all, can I know who are taking this course for credit? One.
Sir, I will clarify the subject matter.
Okay. Okay, you will let me know. So otherwise, 1, 2, 3, 4, 5, 6. Precisely 6. Huh? There's nobody who is missing who actually is supposed to take it. Fine. So my plan is as follows. Today and so day after tomorrow, I'll wrap up the study of spherically symmetric solutions. Day after, I'll talk about black holes again, but this time in somewhat more generality. Maybe more general types of black holes and maybe also some aspects of what is called the Penrose diagram, which helps us to analyze black holes. Then from next week, I'll switch to cosmology. And I will talk about cosmology for the next 5 lectures or so, and then I will actually stop. On 12th of November will be the last lecture of this course, unless there are some extra ones in December, because I'll be busy after that. Now what I propose for the 6 people who are, I don't want to take too much time here discussing it, but for the people who are registered, I would like that each person do a study project over a period of 3-4 weeks and write a report of 4 to 5 pages, not longer, and give a talk of about half an hour to 40 minutes. It could be on, we'll have to work out the topics. You'll have to work them out in consultation with me, but it could be, I don't know, just to throw out some topics. There could be some, you could talk about rotating black holes, you could talk about anything that I haven't gone into in detail in the course, but is also important in the course, some aspect of cosmology. Or you could talk about formalism and, for example, if one person is little mathematically inclined, they could do fermions in the gravitational field. That's a very interesting field theory problem. So things like that. And then we'll hold seminars around 15th of December. Okay, does this suit everybody who is involved?
15th of December.
Yeah. What happens on 15th of December?
But we're supposed to come back on that day.
Okay, so 15th of December doesn't mean in the morning at 6 in the morning. It could be the next day or 2 days later. Okay, there's some room for negotiation. Huh? Okay, fine. So around that period, we'll make sure that people are back. Don't worry about it. Okay. And if there's some very, very pressing need for me to give an exam, so there should also be an exam, right? This is not the only exam. But I don't want to make it a very long exam because then it means I have to correct it. It's a very simple self-interest. So we'll do some kind of finite length kind of exam just to test some concepts around in the same period. So the details I'll announce, but I just wanted to make sure everyone is self-interested. Great.
Anyway, that will be after 15th of December.
Yeah, in the period around 16th to 21st, 22nd. Also because after that, I think you people have other things to do. Yeah. Oh. Yeah. If you want it postponed further, it would be. Yeah. I mean, it should be over by end of December as far as I'm concerned.
End of December is too far.
Too far. Good. So there you are. What I thought is that the thing. Yeah, just that for you have the seminar and the exam probably in the same. Yeah, okay. So the exam 3-4 days later. So let's do a rough thing. 16th or 17th December for the seminars, and 19th or 20th for the exam. Good. Okay. Now, so henceforth team you wear team union equals. Okay. Now there is a story of raised and lowered indices. So it's really going to be. So this is an issue. Yes. Probably this means that in spirit what I wrote earlier was not such a good. No, this is correct. So T mu is always P plus rho U mu plus P G mu nu. So this equation cannot be wrong. Okay, and it's true also if all the indices on both sides are raised. Okay, but now it doesn't mean that the components of P mu nu will only be P and rho because they will include factors from G and factors from U, which could be non-trivial. So let's decide that. First of all, again we assume spherical symmetry, which is at least consistent with our choice of T mu nu. So our solution that we are looking for is going to be parameterized exactly the same way as before with this.
Sir?
Yes.
With this, while we are trying to solve this equation,
Yeah.
we are trying to find out G mu.
We are trying to find G mu nu.
Solving this equation.
Yeah. But we may find some relation among P and rho also, because there are many equations here.
Yeah. No, what I'm saying that if I don't know a priori what the G mu nu's are going to be,
Yes.
how can I claim that there will be a spherical symmetry?
Yeah. So there may be many. So just as I solved with the vacuum, I solved this equation equal to 0. That time also I can't prove that there is spherical symmetry. I can, in fact, there is not in general spherical symmetry. I am only looking for the spherically symmetric solution. There are many solutions. The one problem with general relativity, because of its extreme non-linearity, is that just because there is a equation, I mean, there's nothing unique about solutions unless I specify many things. I could specify boundary behavior or boundary conditions or some symmetry or something. And if I relax that, I'll get more general solutions. Okay. One of the best ways to realize that is that you just take a metric of a star and perturb it, just poke it in some place. Okay. That will violate spherical symmetry. Of course, then it may become time dependent. It will radiate. It will do all sorts of things. But
spherical symmetric thing and time dependent.
Yes.
These two things are different.
These two things are different. However, Birkhoff's theorem, which I can't never remember the exact statement, basically says that they are the same. Spherically symmetric solutions are all time dependent and of this form.
Isn't that only for vacuum?
That's only for vacuum. So here what we are going to do is to look for a spherically symmetric solution of this form. The reason, again, the motivation is very obvious. We already know this form of the solution in the vacuum, and we are going to come down to the surface of a star with that solution. Now it has to match onto a solution inside. Okay, and the star is spherically symmetric. It's the object we are trying to describe, right? We know that it's spherically symmetric in advance. So we simply put in, I mean, of course, again, it's not an exact description of a star, but in first approximation, a star is spherically symmetric. So we're just trying to find a metric which will have this property that it's Schwarzschild outside and it matches onto something inside. So this is the answers we are going to make for that as before. And the equations are going to be very similar, except that first we need to decide what are the components of P mu nu in terms of P and rho. So given this metric, u mu equals -1 tells me that u mu g mu equals -1. In the rest frame, now let's go to the rest frame of u, which means that u takes the form ut, 0, 0, 0. So then ut squared times gtt minus e to the upper dt, so minus 2 alpha is equal to -1. So we get ut is equal to e to the alpha. So that's the first thing we need to keep in mind. Alright. So in the rest frame, u mu is e to the alpha 0, 0, 0. That means this term has an e to the 2 alpha in the time frame component. Similarly, the other term, okay, so let's, without any further ado, let's just write it. So the first term is e to the 2 alpha, this is tt component, so p plus rho into e to the 2 alpha minus p into e to the 2 alpha, so rho e to the 2 alpha. So it still has the property that the first term depends only on rho, but with a dependent, space-time dependent scaling alpha. Okay, alpha is of course by spherical symmetry only a function of r, and in fact rho and p will also be only functions of r by the same assumption. Okay, Now let's look at the RR component. In the RR component, this is 0, and this will just give me P e to the 2 beta. Then theta theta component gives me P times R square, and this gives me P R square sine square theta. So this is T. Now one slightly unfortunate thing is that earlier in vacuum we could solve R mu nu equals 0, because if this whole thing was 0, then by taking the trace we found that R mu nu itself is 0. But now it's non-zero, so we have to calculate the whole left-hand side of this thing. Or we can recast the equation as R mu nu equals some combination of t's, but either way it's an extra complication. And so I'm just going to write down. I might have mentioned that G mu nu is the notation for R mu nu minus a half G mu nu R. And it's not to be confused with any metric. And in this system, GTT is 1 by R squared e to the 2. You can check that these equations reduce to the ones in your notes if you take suitable linear combinations. Okay, so GTT is actually RTT, which is in your notes. So you might have R upper T, lower T, then you have to lower it. Then you have to calculate R from whatever you have in the notes and then subtract these. So you should find these expressions. This is GTT. Then GRR is 1 by R square 2R alpha prime plus 1 minus e to the 2 beta. And G theta theta is R square e to the minus 2 beta. So it's not very particularly simple. G phi phi luckily is just the same as G theta theta up to a factor. So it's G theta theta times theta. And it's no surprise, spherical symmetry will imply that the theta theta component of this equation and the phi phi component are the same equation. So you don't have to do them twice. Okay. So now what do I have to do? So the TT equation sets all that GTT equals rho e to the 2 alpha, and you see that e to the 2 alpha cancels on both sides. Okay, so we get 1 by R squared e to the minus 2 beta of R 2 R beta prime minus 1 plus e to the 2 beta equals 8 pi G rho. So here's an example. This is one of 3 Einstein equations. There will be 3 because TT, RR and theta. So I hope this one is very clear. The second one follows suit. It is 1 by R squared. In the second one, the RR equation, this is equal to that. So we bring e to the minus 2 beta on the other side. So this equation also has the same opening factor. Then it is the rest of it is also rather similar. And this is 8 pi Gp. Now the theta theta equation can be written out, but it turns out we won't be needing it. Okay. The only thing I'll mention here is that in principle these are second order equations because R mu nu involves second order derivatives of the metric, but we could be lucky, okay, because we parameterize the metric in a particular way in terms of alpha and beta. So it could be that the only derivatives which show up are first derivatives, and you see that's the case. These are first order differential equations, which is nice. G theta theta turns out to be a genuine second order differential equation, which is not at all so nice. This you can actually tell from here. You see there's alpha double prime here. So it will be a second order equation. So instead of that, this particular derivation I've taken from Sean Carroll's book. I suppose he's taken it from somewhere. Instead of using the third equation, we'll also use d mu t mu r equals 0. If you think about it, d mu t mu nu is 0 for all values of nu. That's the conservation, covariant conservation of the energy momentum tensor. But in this system, this is going to differentiate something like rho or p, and also there will be a connection term gamma times t that will involve g, okay, and first derivative of g also. So in fact, it will be a first order differential equation involving all the variables of interest to us, alpha, beta, p and rho. Okay, and it turns out to be independent of these two. Therefore, it really corresponds to knowing the first integral of the theta theta equation. That's good. So these are all three first order equations, which is why we have. Yeah. So this is this will be an equation. This is from inspection equation relating alpha, beta, p and rho, because p and rho are the components of t, and alpha and beta occur in the affine connection term gamma, which is in the definition of t. Okay, and it's first order, so it's a first order equation. First order because it only involves the Christoffel symbol gamma, and gamma has only first orders and derivatives. Okay, so we'll take this to be equation 1, this to be equation 2, and this to be equation 3, which I still have to write out in detail. The point is that this will be a substitute for using the g theta theta equation. Okay, being first order, that being second order. That is this. Okay. Now, many good things are happening for us in this system. First of all, again, it didn't have to be so, but the first equation doesn't even involve alpha. Okay, it's only an equation between beta and rho, so it determines beta in terms of rho. That's great. So let's get that out of the way, and then worry about the others. Actually, then we can also see what will happen. In this equation, beta is already determined in terms of rho, so alpha will be determined in terms of rho and p. The third equation, however, will so let's find out what the third equation does later. Let's go step by step. Now, to solve one, by the way, one of the reasons I'm doing this on the board, you can look up these kind of things in books. One of the reasons is to stress what does it teach us about how to solve Einstein's equations. Okay, these are absolutely baby class Einstein equations. They're just next in complication after the vacuum ones. Okay, there are many more. The question is, how do you proceed? What do you look out for? Do you just take this thing and wonder how to change variables and so on? In fact, because it's a physical system, it keeps giving us guidance what we should do. Okay, so the guidance in this case is that we know the solution to solve one. We know the solution for rho equals 0, because we've already solved it in a recent class. And the solution there is that e to the 2 beta is equal to 1 over 1 minus 2 gm by r. Right? Therefore, where m is a constant, capital M is a constant, change variables from by defining, this is an ansatz to help us solve the equation. e to the 2 beta r. Okay, this will confuse you because this is in another system, right? So this is not e to the 2 beta for us. This is just a side comment. This is what it was in the beta vacuum, in the vacuum solution. Okay. Our beta will simply take e to the 2 beta and define it to be 1 over 1 minus 2g m of r over r. So that changes variables from beta of r to m of r, a new function, which we still don't know. What's the benefit? If it's a vacuum solution, when rho is 0, m will be constant and equal to capital M. Okay. Therefore, it's plausible that the equation we get for small m of r by substituting this into this will be simpler than this equation. Understand? When you know an equation for a solution of an equation for a particular case, it also suggests you a change of variables. Is that clear? It's a good change of variables. Anyway, it can't hurt. You can always try it, and it's worth doing. It's a few lines of calculations which are there in my notes, and you find that under this, LHS of 1 simply becomes 2g m prime of r over r square. This whole stuff under that substitution becomes this. Indeed, as predicted, if there was nothing on the right side, then it would set this to 0, therefore m prime would be 0, therefore m of r would be a constant, and that constant would be given the name capital M. So it's all reducing as it should. And therefore we have, now notice also that capital G drops out from the equation on both sides. Okay, so we see that m prime of r is equal to 4 pi r squared rho of r. And this is easily integrated. So this is m of r is 4 pi integral dr r squared from 0 to, so this is a dummy variable r prime, and it's integrated from 0 to r. Alright? So we found m, therefore we found beta. Now can someone give a physical interpretation of m of r? It is apparently the mass, and yet it's not. It's a very strange quantity. So this equation I can erase because we've solved it. This equation I'm going to erase, but we'll have to use it, we'll have to bring it back. So anyway, for now I'm going to erase it. And the last, we'll bring these equations back when we need them. So why do I say that this is the mass or it's not the mass? Well, okay. So it looks like m of r is the mass contained inside a sphere of radius r. It's a reasonable quantity to have. Okay, it's very much like what happens in electrostatics, where the quantity appearing when we try to find a regular solution for a charged body with some charge density is that the field is sourced by the amount of charge inside the sphere where we are probing the field. So something like that. However, okay, before I go on and forgetting about the interpretation, let's notice that if r is the matter radius, I've introduced this quantity earlier, so that there is vacuum outside that. That would be the case when T mu nu, all components, namely P and rho, vanish for r greater than r tilde. Then m for any r greater than r tilde is the integral 0 to r tilde dr. So after r crosses r tilde, this parameter m becomes a constant, and now we know what that constant should be, right? Because that constant is the constant appearing in the Schwarzschild solution, because that's a vacuum solution. So therefore, this is actually equal to m, the mass of the star, or whatever the object, or whatever that object is, the total mass. Right. So it looks like everything fits nicely. It's the integral over of the density, and it's equal to the mass. What else could we expect? Well, there's a small puzzle. For a density rho of R in the given space-time, m should be equal to, the mass should be integral d3x root det of the 3 metric of R. Now this doesn't really seem to give us what we are finding, because the 3 metric is just the part of the metric by ignoring time. So G3ij is just what I wrote before, except, so it's e to the 2 beta r squared and r squared sin squared theta. So root det of this G is equal to r squared sin theta e to the 2 e to the beta. And therefore mass, so I need a name for this. So let me call this m tilde. Therefore m tilde is equal to integral dr r squared. The integral over d theta d phi sin theta gives me 4 pi, that's as before. But there is now e to the beta of r, rho of r. And in fact I know e to the beta of r, so let me put it in. And this should be up to no, not from 0. In fact, I don't think I wanted to do it from 0. I wanted to do it from my signs, right? Maybe I want, probably I want the mod. I want it from 0, but I want the mod because it's the mod of. So it's quite a, so this is perfectly okay. You can factor out root r from it and write it as root of r minus 2gm. I think the integral will exist. The interesting thing that you can see from this is that this quantity is strictly greater than m, the true mass. Okay? Because at every point r, this factor is enhancing the integral.
The upper limit is R tilde.
The upper limit is r. So now let's try to give names to these two. So m is of course the true mass of the star. There is nothing to argue about that. M tilde is the mass that you would get by adding up the density of all the matter that it's made up of. Okay. So why is the mass of an object computed by adding up the density of all the matter of which it's made? Why would that be different from the actual mass of the object? Energy, binding energy. Okay. So if I took the matter making up the star and put it all far separated at infinity, each piece infinitely far away from each other piece, and assemble the total value of its mass, I would get m tilde. But now to bring it all into the center and assemble it into a nice spherically symmetric thing takes some energy, and that cost of energy is m tilde minus m. So it's the binding energy, and the sign goes the correct way because the mass of the object is less than just the mass of its constituents by the amount of the binding energy.
Does this happen for charge system as well? If I have a charge distribution, because I mean, if I have a separated charge in
Yeah, it does.
the factor is.
But 1 minute, if I have a system of charges
Then
and
gather together, the total value will be same.
yeah, so what have you? Right.
Energy.
Sorry, are you asking if there's a binding charge? Okay,
Ah,
there is no
that
binding
kind of,
charge.
yeah.
There's a binding energy even for a
Yes,
system
binding
of charges.
energy.
Okay, but there's no binding charge. No. So this is a unique, if you like, nonlinear effect due to the nonlinear nature of gravity. That's correct.
This is because mass energy equivalence.
Yes. Yes, basically.
So when the masses are very far apart and when we assemble them, I mean the gravity will do that itself. I need to put extra energy, so do positive work on them to assemble them, right?
If they were okay, sorry. Actually, I'm having a bit of problem with my signs again.
Yeah, so
It looks to me that since the gravitational force is attractive, I would have to do work to take them to infinity.
yeah, but
Rather than the other.
The sign
Yeah.
will be.
So that's why I'm very confused. So maybe I've got my sign wrong. So let's just see what is the value of this denominator.
normally binding energy is defined as you have a bound system and
Ah.
how much energy you have to put to take the constituent
Probably
partial.
m tilde will be
Yeah,
defined with a
that's
line.
fine. But it could be of either sign. Okay, it depends on what kind of system I have, and depends crucially on whether things are attractive or repulsive. I have a feeling m tilde is less than m.
Yeah, that what should be able to.
Because this denominator is r minus 2gm, right? Basically, and r minus 2gm varies from 2gm to 0. No, it's not
GM
obvious.
is greater than or less than 1?
No, it should be less. It has to be.
Yeah, I'm very confused now by this thing. This should be from 0 to r. This is the denominator factor because e to the beta is that. And somehow I've convinced myself that m tilde is greater than m, but I'm not so convinced anymore.
Indicate the mass when they are apart.
M tilde should be the mass when they are apart.
And when you actually to let them come to that, actually gain some extra energy.
Yeah, because it's an attractive force.
Attractive force.
Yeah.
So m tilde has to be sum of the energy extra that you get plus the mass.
No, m is the mass of the star, is of the assembled object.
So assembled object.
Yes. Then it is correct.
Yeah, but putting the object
Okay. Why is it correct?
you extra
M is the assembled star.
Yes.
And the other one is disassembled.
Yes,
So
correct.
assembled was must have
Why
is
you get gain energy? You gain energy by letting them fall. You can gain energy and you
so
can
mass should be less.
Mass of what should be less?
Assembled object. Less from the effort. Yeah. that's-
No,
That is what it is.
Good.
That is what
Okay.
it is. Mass of that.
But is it actually from this integral? Is it obvious?
Yeah.
It is obvious because whatever it is, this is no. So this, for that, this should be a factor greater than 1, right? But is it greater than 1?
Indicate should be less than 1. That should be less than 1. I mean, physical ability should be greater than whether it's coming from the integral or not.
I think we should take a vote at least. You are just smiling. You're not giving. What's your opinion? Come on.
So this is right actually.
Oh,
Why you feel because suppose you have a separate mass of a hydrogen atom and a electron,
Yeah.
and you do the total
Good.
rest mass.
Very good.
Let them form atom. It's first it was replaced.
Correct. So
After
it's
years,
less. Yes.
this
Good.
is-
So for an attractive force, the binding energy is positive, which means the mass of the assembled object is less. Yeah. But now, therefore, this equality m tilde greater than m should be true. But is it true from this formula? Suppose
MR itself depends on rho. So
yeah, it's rather complicated to see, so it may not be easy to see. So I think maybe the only thing I'll withdraw is that it's not obvious to me why this inequality is.
Yeah, but it is consistent.
It should be consistent, yeah. But it should still be easy to see in the sense, take this, subtract 1, reorganize it, you know the sign of this denominator, it should be possible to see that it's,
Yeah,
yeah?
it should be possible.
Okay, see. So then I think we are all happy and this is the binding energy. This is strictly an aside because the important thing is m. It's just that curiously in this system m comes out to be the integral of rho in a unit metric while m tilde comes out to be integral of rho in the true metric. Okay, that one m tilde you could have predicted, that's the actual sum over density. This one you just get from a formula, it's just a curiosity. Maybe I've even given it too much time. Okay, good. So now that we are done with this, the key result was that m was solved for and it was equal to the integral of rho. So m of r okay. Now having done this, this implies also that beta is solved for. So now we need to plug this into the GRR equation, and that equation now becomes, that is equation 2 as I have labeled it, 1 by r squared, 1 minus 2gm over r. This notation is nice, easy to remember things. 2r alpha prime plus 1 minus 1 over 1 minus 2gm over r. This should be equal to 8 pi g. This is the second equation. Now this equation just involves the first derivative of alpha and that too only in that place. It's extremely nice for that reason. So it can't be very hard to rearrange the equation and solve for alpha prime. So if we do that, we find that alpha prime of r is g by r m plus of by p. So this solves for alpha prime, thereby by integrating this once, in principle we determine alpha in terms of p and rho.
yes. Alpha and beta are the only unknowns here, right?
Yeah. Yeah, well actually they're not. Alpha, beta, p and rho are all unknown. We've just thrown them into the system. Okay. And what we'll see is that, and what you expect is that the Einstein equations determine alpha and beta in terms of p and rho. But you also expect that conservation of stress energy relates p and rho along with alpha and beta, and it should be an independent relation. Okay, because it's a conservation equation. So you may expect that it relates them, and we'll just see in a second that it does. Because of that, we'll also end up with one relation between p and rho. That in turn still doesn't fix both. The equation of state would be the last equation, which would then fix everything. So although we initially started out to find the metric given p and rho, turns out that p and rho also are influenced by the metric. So it's a coupled system.
But we have three equations for 4 unknowns then. So
We have three equations for 4 unknowns, and then the equation of state will make 4 equations for 4 unknowns. But probably we won't be going that far. Anyway, I want to sort of end now. So let me just, so last equation. This could have been the theta equation, but alternatively, I'm going to write the equation d mu r equals 0. It's quite instructive to work out what this is. So this is dr plus dt dr equals 0. There could be term with theta and phi values of the index, but they all, I believe, drop out. Derivatives, ordinary derivatives will vanish because nothing depends on theta and phi. Perhaps let me say that more precisely. Ordinary derivative in theta will act on t theta r and t phi r. Those components are already 0. Okay. However, you may get, that's also true of ordinary derivative in t, which is inside here. But then the connection terms can contribute, and you have to check that for theta and phi they don't. Right away looking at this, you may think that this term isn't doing anything, but turns out the connection terms here are very important. So let's write out all the things we get. This gives ordinary del r of TRR. This is clearly important because every variable depends on r. Okay. The next term you get is 2 gamma r TR. One of them for each of the indices of t. Okay, that makes up this. Then there's del t of TTR, but this is 0 because TTR is itself 0, t being diagonal. Then there's gamma TTR. Now there are actually several terms. Okay. There would also be terms like gamma TTT times TTR, but those have already dropped. Okay. Then there is gamma R T T T T. And this is nice. Now you can see that in this equation we didn't think that we knew that the pressure is going to come in, but here you see that the density is also managed to come. Okay, so this involves everything in the system, and in fact just use the values. Now you have to be careful, these are all upper T's, so you have to raise the components of T using the inverse metric, and when all the dust settles, it gives a very nice equation that P prime of R is just equal to minus P plus rho into alpha prime of R. Okay. So I'm boxing the three equations that we've derived. And this is very nice because these two boxed equations obviously allow us to eliminate alpha prime, and here, as I promised, is a relation purely among P and rho. P prime is equal to simply minus P plus rho into G by R into M plus 4 pi P R cubed. I can't keep writing the dependencies, so you have to remember M depends on R, P depends on R, rho depends on R. Moreover, M depends on R because of this relation. So finally M is determined purely by rho. So it's an integral function of rho. So this depends on rho, this depends on, this is P and this is rho, and everything else is explicit. So, and this is P prime. So it's an internal relation within the energy momentum tensor variables. Okay, coming from conservation. But conservation doesn't give us something so trivial as we might have imagined that one or other of them is 0 or something like that. Okay, it's more non-trivial than that. Of course, you can see that this is completely consistent with the fact that everything is 0. We had chosen the energy momentum tensor 0 when we solved for the Schwarzschild solution. And of course, if I put 0 here, that's fine. It's a perfectly good solution. Okay, which is why we didn't encounter this equation that time. Okay, now this equation actually has a name. It's called the Tolman Oppenheimer equation. And it sort of determines the hydrostatic balance or the hydrostatic equilibrium of a star, and it's to be taken in conjunction with this, which just relates the fluid the hydrostatic variables P and rho, you have the solution for M, and this in principle gives you the solution for alpha, and therefore you have the entire metric. Now you can't go any further than this without having some idea what kind of material you are using. Okay, there are many kinds of material you could use. One interesting material would be to think about what if this was a cosmological fluid, that is, it was due to the cosmological constant. Then P plus rho would be 0, so this would be constant, so then this is trivially solved by constant P, any constant P and rho obviously, but you could still then find alpha, you have still found alpha and beta for that system, which I think basically is one of your homeworks. So I think I've solved your homework assignment here. This is one of the questions in the written homework. Secondly, you could imagine some other equation of state, which could be, so people talk about equations of state of various kinds, but the point to emphasize is this is nothing to do with gravity, this is to do with the behavior of that particular fluid. We've not said anything, so it's surprising we've got so many results without saying anything about the fluid at all, except that it has a pressure and a density, and is in that, and it has that form of T mu. So for example, people talk about, I don't know, I saw this one, P is proportional to some power of rho. So P is K equals to gamma or something. Such a thing would allow to solve completely, in principle of course, for the metric of the star. Another way would be to say it's incompressible matter, in which case you insist that rho equals constant for r less than r tilde and equals 0 for r greater than r tilde. Turns out that in this case you can quite easily integrate this equation and find P. Okay? And once you are done with everything, you can even integrate that, and basically you can write the entire explicit metric of an incompressible star. But I decided that it's too much work to do in class, and probably doing the integration won't teach you anything new. The important new things are these equations, and now you can plug into them any factual assumptions you want to make about the matter making up the star and find the metric of the corresponding. The nice thing, I suppose, if you do the example, okay, two things, two final comments. One is that I think it's pretty manifest here that this, whatever you get here will match smoothly onto the vacuum solution. It has the same symmetries and in fact has pretty much the same form, and anytime any of these things vanishes, for example outside some radius r equals r tilde, if you want to make the density and pressure vanish, what will happen is that m will turn into a constant there because it will be the total mass, and everything else will be 0, and the equations all become quite easy to integrate, and you get back the Schwarzschild solution. So it's quite easy to see that it matches smoothly whenever r comes below r tilde, it matches smoothly onto this. That's one comment. Yes.
It matches with the vacuum solution outside the matter.
Yes.
Is it an accident or something we have introduced somewhere in our derivation?
I think it's basically built into our derivation because we've solved an equation for which the matter thing is a special case, right? The vacuum solution is a special case. It is the special case when P and rho are 0. Okay? And now what we're saying is that when we are beyond r equals r tilde, P and rho really are 0 by definition of r tilde. So it has to match. Okay? How smoothly it has to match, I can't say. I don't remember. This solution in particular is very explicit, so it's nice to work this one out for the incompressible case. But it may or may not be realistic. Anyway, there was one more comment, but I can't remember. Yeah, okay. So I'll stop with that. And as I said, next time I'll talk about the spherically symmetric solutions for the last time, and then we'll talk about cosmology. Yeah. Gravitational radiation. Actually, I'm wondering whether gravitational radiation could be one of the topics for one of your projects. We're running out of. I've gone very slow in this course. That's the reality. But we're running out of lectures. In the worst case, one lecture on gravitational radiation. Let's see. We still have some time. So.